I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. I'm Taylor Sparks. I'm an associate professor in the Department of Material Science and Engineering here at the University of Utah, and I'm joined by my co-host, Andrew Falkowski. And this week, we're also joined by Marie Jackson. She's a research associate professor in geology and geophysics here at the University of Utah. She's also the creator and co-founder of the Surtsey at 50 Years, a blog that has to do with the drilling and research on Surtsey volcano. Marie, welcome to the show.
Hi, thank you.
Well, we're excited to have you here. We always do a lot of research in getting ready for these shows, and actually finding Marie was a bit of an accident. We were Googling about the history of concrete, including Roman concrete, and we stumbled across all these articles referencing this individual right here at the University of Utah. So we're thrilled to have her contributing on this episode. She brings a ton of knowledge and a wealth of expertise. So to get started, we're going to dive into the concrete basics. Andrew, why don't you get us going?
Yeah, I think before we really get started into the process of how we make concrete or where it comes from or even the history of it, I think we need to define a couple of terms just so that everybody's on the same page. So when we're discussing concretes, we think about it in terms of there being a binder and a matrix. Now, it can be a little bit more complicated than this, but in simple terms, this is sort of what the gist of what concrete is all about. So in this case, your matrix tends to be a very solid material that can kind of form a network or a structure. And your binder material will bind and hold this structure together. And so the combination of these two things is sort of the foundation of what gives concrete its strength and how it works on a very simple level. But beyond that, there's a lot of other terms that we need to discuss. One of the big confusions that seems to arise is the difference between concrete and cement. And I think Marie's a little more apt to explain this than I am.
Well, concrete is a massive material composed of sand, gravel, large aggregate that is bound together by a cementitious material. In modern concretes, this cementitious fabric is formed by Portland cement. Cement is a material that is essentially burned up rock, limestone, and maybe some clay-rich rock, among other things. When these rocks are burned, they form a material called clinker, which is vitric in composition. And when this is ground, it forms a powder we call cement. Cement is one of the components of modern concrete.
Okay, so now that we kind of have an idea of some of the main terms, and we're going to define a few more later on, why is concrete such a big deal, Andrew? Why do we care about it? Why is it worth a whole episode? And why is it called the ultimate construction material?
Well, it allows us to do a lot of things that other construction materials simply do not. For one, it's very hard and has similar properties in terms of its strength to stone, but it's also very moldable and pourable in that we can mold it to meet all these different complex shapes and build structures that wouldn't be possible if we were using brick or wood. And so, going back and thinking about all the amazing structures that the Romans were able to build with this material, and thinking about all the amazing structures we can build now, today, because of this material, it really shows throughout all of history that it is the ultimate building material, and its both versatility and properties make it so as well.
And they use it also because of its cost. A synthetic sort of form of stone that can be flowed, that's important. But to be able to do that at a low cost, this stuff is something like $100 to $125 per cubic yard, right? That's very, very inexpensive. Something like 10x or an order of magnitude cheaper than most other construction materials that you might be looking at. It also has some benefits in that it's relatively fireproof. Fire will degrade it, but it's relatively fireproof and relatively flood-proof. Right? And this is why it's not surprising to learn that it is probably, to my knowledge, the most widely produced man-made material on the planet. There are 4.4 billion tons of concrete produced a year, and they predict that this is going to go up by the year 2050 another 25%. So this is a big deal. It's more than 2 times more than all of the steel, wood, plastic, and aluminum combined. So this is a massive thing that we produce, and it has important economic and environmental implications. For one thing, the market for ready-mix concrete is $600 billion annual, right? Put that in comparison with like smartphones, which we know are a big driver of the economy. Those are only $500 billion. So this is a big deal. Now, what about CO2, Andrew?
Yeah, so the process of making cement, now there are many different types of cement and the processes differ between them, but the very common Portland cement that is used a lot in the modern world, this is tied to about 8% of the total CO2 emissions worldwide. And that's really only accounting for just the production. When you consider that there are additives such as steels that are introduced, such as rebar, those also take some amount of CO2. And so it actually is a major contributor to CO2 emissions. And when you consider the fact that as the third world starts to develop and they're going to need more structures and they're going to use that, there are going to be even more CO2 emissions from the production of cement.
Another big advantage to it, when you think of like a big concrete block, you think that that's really heavy, but in fact, the density of it is relatively low. The density of concrete is something like 2.3 grams per centimeter cubed. Let's compare that to like aluminum, which is 2.7. You've got a material which is lighter than aluminum, much lighter than something like steel, which is around 8 grams per cubic centimeter. So it's actually relatively low density for the versatile material it is. Okay, Marie, oftentimes in common literature, we always see people talking about cement drying. Can you dive into this a little bit? Does cement dry? And if not, what's actually going on?
Well, cement is the raw material that we purchase in the bag at the hardware store. When we mix it with water, many different reactions take place that are mainly hydration reactions that form a paste. We call that a cement paste. When that paste goes through the process of hydration, a very important material forms called calcium silicate hydrate, CSH. This is essentially the glue of concrete materials. It has a layered structure and it binds the inert sand and gravel of the concrete mix.
Yeah, I remember, so I worked in construction one summer when I was in high school in order to help sort of pay for college. And I remember we were pouring concrete for a house foundation. And actually, my boss, I guess he corrected me because I said, how long is this going to take to dry? And he corrected me to your point that it's not drying. The term is, I believe, set. The concrete sets, or the cement will set over time.
Mm-hmm. Yeah, actually, you'll hear about concrete setting up. And while it might look hard to the touch and finished and ready to walk on after, say, 24 hours, it actually continues to set up over long periods of time. According to industry standard, it's at full strength at 28 days. You're reaching about 70% of your strength at 24 hours. But in fact, this can go on for years. Andrew, you were saying something about the Gardner building being constructed.
Right, yeah, that was built a couple years ago, and it's crazy to imagine that on a very imperceptible level, the concrete that was used to make that building is still hardening today.
Okay, when you go to the hardware store and you buy a bag of Portland cement, first off, we should realize there's actually lots of different types of cements. If you just do a quick Google, there's something like 13 different types of cement, and they might be more tailored for different uses. Some might have excess of a certain type of element like aluminum or different types of other things. Portland cement is not named after the city Portland. It's named after the mineral. In the early 1800s, there was a guy named Joseph Aspdin, and he was mining Portland stone from a quarry in the Isle of Portland in England. And basically, he used this early form of essentially lime, calcium hydroxide, to make the version of cement that he was using. And that's actually quite different than modern Portland cement. Modern Portland cement is going to start with calcium carbonate limestone. It's going to take rock-containing silicate minerals, things like clays, right? You're going to get your silicon, maybe a little bit of aluminum in there. You're going to fire these things at a high temperature. In the process of firing them at high temperature, the calcium carbonate is going to give off CO2. That's where the carbon footprint of cement is coming from. Calcium carbonate converts to lime, calcium oxide, and it gives off CO2 in that process. You take this remnant, you grind it up. Once it's ground up, you have something that is now cement.
Hearing that reaction, it can be a little confusing to try and visualize what's actually sort of going on here. So a really simple, I guess, sort of analogy to thinking about how what the sort of reaction looks like as you're going from the dry cement powder and adding water to it is you can actually think of Jell-O or jelly. if you have experience with that, you'll know that there is this underlying sort of structure that holds it together, and within it is a bunch of water that's trapped. Well, the same sort of thing is happening with cement as you add water to it. We have this internal skeleton that traps water within it, and what's happening is that the CSH forms a very layered structure, and what happens is these CSH fibrils will form from this and propagate, throughout the structure as it continues to react with water, and eventually that's how you'll form this solid binder when all of the water has reacted.
Now, it's interesting. This is basically forming the binder that's going to hold all this aggregate together, but you can actually tune the amount of water to the cement ratio, right? So there's something called Abraham's law, which essentially tells you as you make a cement which is thicker because you added less water to it, you get better strength, right? As you add water, it flows better, so it might be easier to work with, but you actually sacrifice strength. But you can also tune the other components, right? You can add less or more sand or gravel, and this allows us to make some interesting types of concrete. For example, there's something called pervious concrete. Pervious concrete is one where you have the binder, right? You're having cement, you're adding large gravel aggregates, but you're not adding much sand. And so you end up with, if it looks sort of porous, and that's the point, it's pervious, so that when it rains, for example, you can get water washing right through the concrete. And so this allows cities to have sort of innovative ways to manage stormwater and things like that. And it makes for good walkways, greenhouses, places where water is going to be accumulating. This prevents it from accumulating on the surface because it can pass through the concrete.
It's amazing that you can make such a very you can use this material is so adaptable that when you're building structures with it, you don't have to interchange different types of materials. It's only just a difference in composition.
Okay, Maria, I had a question for you. We just we're getting a shed built in our backyard, and so we've been talking with people about putting down a concrete pad and all that. And one of the people I talked to was saying, the best way to do it, the strongest would be to just put Portland cement and mix it together. Don't add any sand or gravel. Is that actually true?
Well, that would actually be building something out of a cement paste. You would have to rely on that cement paste for all the material characteristics of that pad. We add sand and gravel to add additional strength to the concrete mixture.
So if I was thinking, let's say I was making a chair might include wood and also the wood glue holding different parts of it together. What this person was proposing to me to do was basically build the chair out of wood glue instead of including the other components which might be adding strength or other properties.
A good point, yeah.
Yeah, so you talked about this craftsman who is trying to sell you essentially a chair made of glue. And and you talked about the tunability of concrete and how we can manipulate the different ratios of components in order to get concrete of different properties. But there are also limits to this tunability. If you add too little water or too little Portland cement in the concrete, then what's going to happen is you might get some unreacted raw cement within the mass. When you get unreacted raw cement within your concrete, this can be particularly devastating from a structural standpoint. Think about in the 2010 Haiti earthquake, 250,000 buildings collapsed. And when they went back and did an investigation as to why this earthquake was so devastating to the structures of this country, they found that a lot of it had to do with shoddy construction and poor quality concrete where they weren't getting those ratios right. And so what makes this matter even worse is that identifying bad concrete is potentially difficult because a lot of these errors can be internal. So a lot of people speculate and worry that there are a number of structural, almost ticking time bombs throughout the world where the concrete wasn't mixed properly, and if there is some sort of natural disaster, these buildings are very prone to collapse.
So I've got pulled up an article here from The Guardian, which was comparing that earthquake with another earthquake that same year in Chile, where most of their concrete structures were reinforced concrete. And a very similar sized earthquake, you might have expected very similar outcomes, was a completely different outcome because you had a much better concrete that had been constructed due to the inclusion of reinforcement.
Well, in terms of tunability, nowadays, most structures in the United States don't use pure Portland cement in their construction. Instead, that Portland cement is blended with supplemental cementitious materials. This decreases the overall carbon footprint of the concrete structure. And in addition, many of these materials add durability to the concrete through various processes.
So that's fascinating. Can you explain a little more? What are some examples of supplemental cementitious materials that we're using?
One of the most important supplemental cementitious materials through the history of concrete has been volcanic aggregates. This is because those materials contain reactive glasses that interact with portlandite to create a calcium aluminum silicate hydrate binder that has more resilience than a pure CSH binder. Volcanic materials have been used in Portland cement concretes with a lot of success, and these are called pozzolans. A pozzolan is a material that reacts with lime in the presence of moisture to form cementing binding hydrates. You know, pumices were used in a lot of Western United States concrete infrastructure beginning in the early 1900s, and those materials are pretty durable today, over 100 years later. In the 1970s, though, a new material started being added to concrete called fly ash. Fly ash is a fine-grained material that's produced through the burning of coal, and that was a really effective additive to Portland cement concretes over the last 40 years. However, now that we are making big strides in burning less coal
And burning it more efficiently, right?
and burning it more efficiently, there's very little fly ash in reserve in the United States.
So as there's less and less fly ash available, we're going to be looking for other supplemental cementitious additives. And we're not the first ones to do this, right, Marie?
No. We have some wonderful examples from 2,000 years ago from truly brilliant Roman engineers and natural scientists that used volcanic tephras, or ashes, from the central Italian volcanic districts to make truly extraordinary concretes.
Is there any knowledge on how they did this? Was it just trial and error? Like, what is known about their process for discovering things? Did they get better at it over time? I'm just curious. Thinking about Romans as scientists is not something my mind's done before, so this is interesting.
Well, I've actually done a lot of work on that, working with archaeologists and volcanologists in Rome over the years. We've studied a lot of the early concretes of Rome in Republican-era structures, and then tracked the development of the material into the imperial era, which began in 14 BCE. It turns out that Romans went through an extraordinarily productive period in the refinement of their concretes, in particular a mortar that used volcanic ash, between the time of Julius Caesar in 44 BCE to the initiation of the Augustan era in about 14 BCE.
So do we see that by, obviously I know in your work you go out and actually drill cores, right? And you actually investigate the concretes from Roman structures. Is that right?
Well, that's right. Most of those cores come from marine structures. So Romans perfected two types of concrete. One for architectural structures in the large monuments of Rome, and simultaneously, the construction of harbor infrastructure around the Mediterranean. Those were seawater concretes, and they were responsible for the economic and military successes of the Roman Empire.
Now, when you say perfected, is there something that really makes theirs unique and better than other versions of concrete out there?
Right. Well, in principle, Roman concretes are conglomeratic materials. They contain large chunks of rock, limestone, volcanic rock, or even brick, and these are held together by a binder that's based on calcium hydroxide and volcanic tephra. That binder is called a pozzolanic mortar, and this is a very dynamic and sophisticated material, both in the architectural concretes and the marine concretes, that changes over time to provide enormous chemical and mechanical resilience to the structures. So when we look at these mortars, which really hold the secrets of the concrete in Roman structures, in both the architectural concretes and the marine concretes, there are two phases to the cementing reactions. The first phase is one that is called pozzolanic. A pozzolan is a material that reacts with hydrated lime in the presence of moisture to form cementing binding hydrates. So Romans burned limestone to make lime, CaO. They brought the CaO to the building site, and they hydrated this with fresh water in the case of the architectural monuments and seawater in the case of the marine concretes. They specifically chose certain volcanic tephra to react with the hydrated lime. For the architectural concretes in Rome, they used a material from a pyroclastic deposit called Pozzolane Rosse. And in the marine concretes, they used pumices from the Campi Flegrei and Vesuvius volcanic districts, and they actually shipped those pumices all over the eastern Mediterranean to build these enormous harbor structures. What we know now is that the mortars went through an early period of pozzolanic reaction. So initially, the volcanic tephra reacts with hydrated lime, and this produces an extremely resilient calcium aluminum silicate hydrate binder that we've only begun to understand its material characteristics. However, what it was not previously understood is that pozzolanic phase lasts for a relatively short time until all of the calcium hydroxide is consumed. At this point, the chemical system of the concrete changes from one that's dominated by lime and very high pH to one that's dominated by the dissolution of glass in the volcanic aggregate. The pH drops a little bit, maybe to 9 or 11, and through dissolution of the glass, fluids become enriched in silica, aluminum, calcium, sodium, potassium, and new mineral cements form. Romans observed these processes around the Gulf of Naples and described them in ancient texts. And we, as geologists, know lots about these processes in volcanic rocks. It is that post-pozzolanic system that really produces the resilience of the concretes, because new cementitious hydrates in the form of mineral cements can form over time. So if a crack forms, new mineral cements can grow through the cracks and form a kind of regenerative repair over time.
That is so cool.
We have some new publications on this, and we're doing new work through experimental testing.
We're definitely going to put a link to those publications in the show notes if you're interested in reading more. Something that I'm really curious, though, in reading about your research here is that it was known, like I'd heard before, that Roman concrete, this art of making Roman concrete, was lost. In other words, like as with the fall of the Roman Empire, we stopped seeing this really high-quality Roman concrete places. And it was lost for quite a long time. And it's only recently been sort of rediscovered, if I'm using the right word here, Marie. But now you actually have research from, it's not just from a historical perspective we're thinking about this. We're actually thinking about this from a funding agencies are considering this for new next generation's versions of concrete today. Do you want to talk about that a little bit?
Sure. Well, first of all, I would say that the practice of Roman concrete was not entirely lost in Rome. During the Middle Ages, there were a lot of concretes made. We have a record of those. For the most part, they used the same principles as the imperial era concretes. However, their quality control wasn't quite as high. In the marine concrete sphere, however, those big ports weren't really necessary. New ports were not needed as the economic situation around the Mediterranean declined after the imperial era. So we don't really see ongoing development of the marine concretes during the Middle Ages.
So was a lot of the the difference in the types of concrete that was being made? Was a lot of it fueled just by the expanse and like the transportation system that was built by the Romans, and as well as just the economy that driven it?
Well, that's a really good point. I think when we look at the structures that Romans built, it's telling us a huge amount about the efficiency and power of the imperial Roman economic system. In terms of the concretes themselves, Romans were going for specific performance characteristics. They used different mortars and aggregates in the large vaulted domes of the big imperial monuments than in their foundations. And they used a very different mix design and installation procedure in the marine concretes than in the architectural concretes. So these were engineers who had a very firm empirical sense of what performance characteristics they wanted to develop. And apparently the imperial management of construction resources would do whatever it took to provide what they needed for these government-sponsored structures.
So I'm curious, what is the Department of Energy in 2020 interested in Roman concrete for?
Well, the Department of Energy's mission is to wisely use the energy resources of the United States and protect them. Recently, it's become more and more apparent that the production of Portland cement concretes comes at a very high cost for both usage of fuel and the production of CO2 emissions. So the DOE has a new funding call out for extremely durable cementitious materials that greatly decrease the energy inputs into concrete through their production now, and also extends the service lives of these concretes to tens to hundreds of years. So once that concrete structure is made, it persists and doesn't require a new fuel input to build another building.
So one question that I have is, and I'd like to get your opinion on it, having done so much research, is was it that the Romans were very skilled in engineering these materials, or were they just lucky to have so many of these materials nearby, or is it a combination of both?
It's definitely a combination of both. These were people who had extraordinary talents in empirical observation, and we can see that when we read the works of Vitruvius, the 10 books of architecture, or of Pliny the Elder in Naturalis Historia. So these were people who actually used a scientific method. I have a paper on that, of hypothesis and testing. And in addition, they had extraordinarily reactive volcanic tephra deposits, both in Rome and around the Gulf of Naples. And they learned through experimentation that they wrote about which deposits to select and how best to refine the mortar mixes to influence their performance standards.
That is fascinating.
Mm-hmm. And the Romans weren't the first to develop concrete, right? They had seen some examples of concrete in Syria as well. Is that right?
I think it all comes down to how you define the concrete. But if you're talking about like that there's cementitious sort of binding of aggregates, yeah, there's examples that go back to the 4,000 years before Christ era, where they would essentially in the desert build these cisterns. These are underwater or underground water tanks. And the concrete, it's impervious, being impervious to water was the only reason that this society could have survived under those conditions. So it was sort of designed based off of what the conditions were requiring them to come up with.
Hearing about these Syrian cisterns and then hearing about the Roman structures, it seems to me that the Syrians were using this concrete what is similar, analogous to concrete, out of necessity. But when I think about the Romans, was it a necessity on their part as well?
It really was. Early Republican Rome was made out of dimension stone, and that dimension stone was principally volcanic tuff. In the 10 books of architecture, Vitruvius laments the quality of this tuff. It's soft, it's friable, it falls apart easily, it needs to be covered with plaster just so that it can survive. So when Romans began to build a capital city, they needed a very different material to work with so that they could construct the kind of architecture that was representative of the center of this empire. And I think that that was one of the underlying motivations for perfecting concretes, given the very poor resources in their geologic environment.
So to fuel a great empire, you need an equally great material. And certainly, if you think about aqueducts and all of the transportation that they needed to move supplies or move armies across all the lands that they had, concrete would have been a necessity.
Yeah. So as I'm hearing this, so far, concrete to me is sounding like a pretty magical material. I mean, think it's a synthetic version. It looks and acts a bit like stone, but it's low density. It can be cast into lots of different shapes. We've discovered that it's cheap, relatively corrosion resistant. It can withstand lots of problems. It sounds too good to be true, but it has a crucial flaw. It's weak under tension, right? Now, the compressive strength, if you look at it, is something like maybe 17 to 28 megapascals, typically, although you can make specialty concretes which are even stronger. But the tensile strength is far, far lower, something like 2 to 5 megapascals, making it basically the same stress that would cause polyethylene to start bending can break concrete under tension. So this is a huge problem.
In Portland cement concretes, cracks propagate mainly along the interfacial zones of the aggregate with the cementing paste. This is because that aggregate's inert, and those surfaces often have voids in them and are susceptible to detachment from the cement paste. Once the crack begins to propagate, there's not very much in its way that would force it to stop propagating, and so it becomes longer and longer and can carry more and more displacement. This can lead to serious structural problems associated with fracture in Portland cement concretes. In Roman concretes behave in a very different way. Remember that the volcanic tephra used as aggregate is very reactive. And what we have found in our experiments using actual Roman tephra, Pozzolanic Mortar, in a hydrated lime system is that those surfaces grow new mineral cements. Those surfaces have mineral cements that protrude from the tephra into the cementing matrix. These can have fibrous or acicular forms or platy forms. And in fact, they form obstacles to the propagation of microcracks. So that when cracks form in Roman concretes, and they do a lot, it just requires far more energy to make the crack grow and into a surface that can carry very much displacement. So if you go to the monuments of Rome, you will see many, many cracks, and you will see intact structures.
That's fascinating. So an alternative approach to this that was discovered, which we'll talk about after the break, has been to rely on reinforcing concrete. And to go back to the example of the Haiti versus Chile earthquake, it can lead to massive differences in the performance. So we're going to jump to a quick commercial break, and then we're going to come back and talk about this process of forming reinforced concrete. Materialism Podcast is sponsored by MatMatch. If you haven't heard of MatMatch before, it's a platform that helps engineers find the materials they're looking for, that has the properties that they're interested in, and then it helps them identify suppliers that can actually produce those materials. So today, since we're talking about reinforced concrete, let's go to matmatch.com, and I'm going to type in concrete. Now, while they don't sell concrete in its finished form, they do sell a lot of the components that go into concrete. What I'm going to select here is a lot of the steels that go into the steel reinforcement. What's great is it lists a whole bunch of different grades right off the bat. What I'm going to do is I'm going to click the compare button. In today's episode, I'm going to show you how we can compare different things. So as I go down this list, comparing different materials, when I select the compare at the end, what pulls up is the ability for you to plot for many different materials how their properties compare. And you don't have to plot just one property at a time. For example, I'm clicking density, elastic modulus, yield strength, elongation. All these properties at once, they show up in what's called a radar plot, where you can actually see how they compare across multiple different categories, because it's rare that we want to optimize a material based off of a single property, say density. it's much more common that we care about density, but we also care about strength or elongation. And using this comparison feature on their website, it makes it really easy to pick just the right material for a given application. So if you haven't checked out mapmatch.com, go see for yourself how easy it'll be to use on your next engineering project.
Okay, we're back from the break, and now we're going to discuss the emergence of reinforced concrete. Now, in the Middle Ages, after the fall of the Roman Empire, the art of making this very high-quality Roman concrete was seemingly lost. And crack propagation, as Marie was describing before the break, is a huge issue. Now, the Romans had a way around this, but a lot of the modern concretes that we had suffered from this problem, and it wasn't until the European Industrial Revolution that we got a solution from a very unlikely source. Parisian gardener Joseph Monnier, and he was interested in making his own plant pots. He wanted to grow a bunch of these very tropical plants that were very large in greenhouses, and buying clay pots was incredibly expensive, and they're not strong enough to hold these giant plants. And so he was thinking, I could make this out of concrete. And so he did. And one thing that he noticed was that, when things cool down and heat up, they contract and they expand. And when water gets in there and it freezes and contracts and expands, it can lead to this crack propagation. And so all of his concrete pots kept shattering. And so he came up with this ingenious solution, and he had no way of knowing that it would have worked, that if he just took some steel wires and put them within the cement paste as it was setting, then these would potentially provide some sort of structural reinforcement. Now, this worked beautifully. They did provide that structural reinforcement. He didn't see nearly the same degree of crack propagation. But what was even more amazing, and that he had no way of knowing, is that the steel wires that he used to reinforce this had almost the exact same thermal expansion coefficient as the concrete itself, which meant that as the concrete heats up, it expands a little bit, but so will the wires. But they expand at such the same rate that they wouldn't destroy each other. And what's really interesting is I think it almost had to be someone who wasn't an engineer or related to this to actually come to this solution. Because if you think about it, putting steel in concrete, you think that their thermal expansion coefficients would be so different that they'd tear each other apart.
Typically, ceramics have a thermal expansion something like 10-ish ppm per K, whereas metals are typically between 10 and 100. Polymers are typically over 100. It's sort of like this order of magnitude increase. So I certainly wouldn't have expected that. It's really interesting. And yet nowadays, putting things like steel inside concrete to make reinforced concrete is the standard, right? You'll see this all the time where they'll add these things along it. And they typically do it not with wires, but nowadays we use rebar. And if you've seen rebar before, it has that sort of grooved structure on the outside. Those grooves are to increase the ability for it to bond with the concrete, right? It gives it more surface area. If it does start to debond in a certain spot, as it pulls out, it's going to make it harder for it to debond and come out of there. Now, if you just add the rebar to concrete, cracks are still going to form as it goes under load. But once it's put under tension, the rebar is hopefully going to carry the tensile load. And when it's loaded under compression, now the load is going to be transferred back to the matrix, which is the concrete. But there's something else we can do to make this even better. There's something called prestressing. So in prestressing, let's say we make our mold that we're going to pour our concrete into. We put our rebar in it, and we're going to stretch that rebar ahead of time. So we're going to pull it and put it under tension. Then you cast your concrete around it, let it set, and then you release the stress on that rebar. When you release the stress, it's going to want to shrink, and as it shrinks, it places the concrete in a pre-compressed state, which is where it wants to be, because remember, concrete is stronger under compression than tension. So before it can break due to tension, it now has to first overcome the compressive load that you've pre-stressed it with. So pre-stressed concrete is a way, any sort of bridge overpass, if you see these are all pre-stressed to give them much greater tensile strength.
Yeah, well, one thing to think about with steel reinforcement in Portland or blended cement concretes is that the way that steel stays intact is through the ongoing persistence of calcium hydroxide in the system. This keeps the pH high, around 12, and it forms a passivating layer on the steel so it doesn't corrode over time. Maybe some of you have seen concrete structures that are turning red and sort of bleeding red, especially in seawater structures along waterfronts. Those are places where the concrete has been attacked by different chemical processes and the steel decayed or corroded because of this absence of passivating hydrated lime or portlandite in the system.
Yeah, that red is the same rust. It's the same red of like rust. It's iron oxide that's essentially leaching out now because your iron is now corroding. This is a great segue to our next topic, which is degradation of concrete. We'd like to imagine it's this perfect material that doesn't corrode or degrade, but there are some degradation pathways with concrete. And the first one we've just described, that if you start to form iron oxide because you've lost this protective portlandite layer on the steel, that's one problem. What other types of degradation do we see with concrete and cements?
Well, especially regarding that protective layer, it's easily eaten away by salts. And so as you were discussing with marine applications, we're seeing that rust that's coming out. The salt water easily can penetrate that protective layer and start dissolving and corroding the iron in it. But what's also interesting is that the salt that we put to melt down snow as well can also get in there and have a similar effect.
I know, because my dad would never let me use it growing up. I had to go out and shovel the ice off. He wouldn't let me melt it because he didn't want to destroy our concrete. This is actually an interesting idea. So with freezing, ice forming, right? Freeze-thaw cycling with concrete can be another big problem. What happens if you have little voids and cracks, water gets in there. As it freezes, it expands. It's going to cause that crack to get propagate a little bit further each time. So this will actually destroy concrete over time. And there's some things you can do to fix this and prevent it. You could first try and seal it. You could seal your concrete with some sort of, in the same way that we cover up metal with paint to protect it from oxidation. You can basically seal out water if you can try and do that. But it's more common to actually introduce air entraining agents into the concrete to protect against freeze-thaw cycles. I'm just going to read this so I get it right. It says here, the general mechanism by which air entrainment improves concrete durability in freezing and thawing exposure is as follows. When water in the concrete, resulting from precipitation or from contact with moist subgrade, when it freezes, it expands, and this movement of water generates pressures that, in the excess of tensile strength of concrete, are going to cause cracking and scaling. Concrete has to be critically saturated, over 91%, which is true for concrete surfaces. Now, the entrained air bubbles are microscopic, so these are really, really small, and they're evenly distributed in the paste fraction. So they take on the water during the freeze cycle, and then in doing so, they relieve the pressure buildup. Generally, an air entrainment agent, we're talking about 4 to 8%. And if you add that, then you can prevent this freeze-thaw damage in concrete.
And this freeze-thaw damage is also very critical affects and impacts the corrosion of these rebar that are in it. A lot of issues that are actually happening now within America is that we have all these bridges and infrastructure, and through freezing and thawing, the concrete has degraded, and these rebar are becoming exposed to the air and the elements, and they're degrading that way. So there's a huge push to try and either come up with, ways to prevent this degradation or coat it such that it won't corrode in this way. But there's also ways of looking how we can pre-coat the rebar itself in ways that when it does become exposed, it doesn't break down, because once the rebar corrodes, that's now your weakest part of your material. And so if there's a bridge that is the rebar is corroding within it, how safe is that?
I think that that's really interesting in terms of this new DOE project. They are actually interested in finding innovative concretes that don't use steel reinforcement for these very reasons. And that's part of the Roman model of concrete, is that Romans did not use steel reinforcement. Instead, they packed their coarse aggregate, which are big chunks like as big as your hand, and they packed this in a way that geologists call conglomeratic. So there's a three-dimensional framework of rock in the concrete that holds the structure in place. And one possibility is that we may be able to create Roman-type concretes for certain aspects of these bridge components that don't use steel reinforcement and could persist for much longer periods of time.
Yeah, for any rock climbers that might be listening, there's a famous canyon here in Utah called Maple Canyon, which is full of conglomerate rock, and it's giant. You'll see like a football-shaped rock sort of sticking out, and they're just all over the place, which makes for interesting climbing. But this is curious to think about as an engineering material. This could this same type of approach might help produce fracture but without steel running through it.
So in order to address some of these issues like crack propagation, we've started to develop very specialty concretes that can adapt in different ways to their environment and produce, try to address these issues. One of these is self-healing concretes. So there's a couple different approaches to this, but one of the really interesting ones that I found is that they discovered that there are these bacteria that live at the bottom of highly alkaline lakes that are formed by volcanic activity. These have pH levels between 9 and 11. And it was previously thought that bacteria couldn't even exist in these sulfurous ponds just because it was such a toxic and harsh environment that no life could exist there. But upon further investigation, they did find these alkalophilic bacteria that could survive. And one particular type called B. pasteuri, probably botched that, could excrete the mineral calcite, a constituent of concrete. And so these bacteria are extremely tough and can even survive dormant when they're encased in rock for decades. So the idea behind the self-healing concrete was that they had all these little bacteria embedded inside the concrete along with a form of starch, which is their food. And so what happens is when a crack propagates or forms, they get released from their dormant state.
Cool.
They eat the starch and then start excreting the calcite, which then acts to heal the crack that has formed. And so they've shown through this that cracked concrete can recover 90% of its strength through this method of self-healing. Now, the Romans also had a method of self-healing as well, but it goes by a different name.
That's right. The Romans were using a more chemical approach, and that's the post-Pozzolanic processes that we described earlier, where the ongoing beneficial corrosion of glass, so the dissolution of glass in these very massive structures, either architectural or marine, causes new mineral cements to grow on the surfaces of the tephra and in cracks that have formed. These post-Pozzolanic processes in some aspects resemble alkali-activated processes in modern concretes or even geopolymeric processes in modern concretes. But there's something else that's very interesting here, especially from a geological point of view. There's a tiny island off the coast of Iceland called Surtsey that erupted from 1963 to 67. It's basalt, which is the most common rock on Earth, and it is actually a geologic analog for Roman concretes, Roman marine concretes. The basalt is actively going through alteration at various temperatures, and it's growing the same mineral cements as Roman marine concretes. A big part of this project is to understand how microbial life influences the alteration of the basalt. We have a project, the Sustained Drilling Project, where we achieved 3 new boreholes into the volcano in 2017. We are looking at microbial processes in the glass that produce mineral cements, such as a very unusual mineral called aluminous tobermorite that can heal cracks in the basalt in the same way that Roman post-Pozzolanic processes heal cracks in the marine and architectural concretes.
That's super cool.
This is so cool. I'm reading about it right now. It's fascinating.
Wow. One last type of concrete that I thought was really cool and is more of an aesthetic sort of thing is this idea of self-cleaning concrete. So if you put titanium dioxide particles on the surface, these are microscopic and transparent. When these are struck with UV light, they emit free radical ions, and these break down any sort of organic dirt or matter that comes into contact with them. And so then the remains can be washed away by rain or wind. And so another interesting benefit, aside from keeping structures very pretty and clean, is that titanium dioxide also acts as a catalytic converter of sorts, and it can help reduce the level of nitrogen oxide in the air.
I've sometimes seen research talks about this where they claim that. Do you know if this is actually commercially available? Can you buy this right now, or is this like hypothetically could be done?
I don't know if it's commercially available, but I know there's a church in Germany, I believe, the name is escaping me, that used it. And you can look at pictures and it looks very clean and beautiful, yeah, as if it was just poured. We're going to do a really short Q&A segment because this episode has gone a little bit long, but since we're talking about concrete, I wanted to pose the question, what are your favorite concrete structures?
I want to hear Marie first.
Thanks, Andrew. I definitely have a favorite, and that's the Markets of Trajan in Rome. This was constructed about 100 CE. It is one of the most beautiful structures. It forms the base of the Quirinal Hill and has a beautiful arched hall, the Grande Aula, that is the prototype for the Pantheon. And it's through our collaborations with archaeologists at the Markets of Trajan that we've learned so much about these really extraordinarily durable materials and how they perform in different states of stress through the monument. So definitely Markets of Trajan. You can visit it. It's an active museum called the Museo dei Fori Imperiali in Rome. Do go. It's beautiful.
That's super cool. What about you?
My favorite, I don't know, I've never actually thought about this, so I need to give it more time. But I'll say one thing that struck to me. I lived in Argentina for a few years, and there's a little mountainous city called Tandil, which has this giant Christ statue. And I remember walking up to it, and it's all concrete. But from a distance, you don't realize how big it is when I got up to it. It was so massive, and to think of something that heavy and massive on that mountain, I thought that was really interesting. So that's probably my favorite right now.
Sticking with Rome, I definitely have to say the Pantheon is one of my favorites. I took a small trip there and got to go and see it, and it's really hard to appreciate the true like magnitude of this dome that's freestanding, unsupported for 2,000 years. And even it has cracks in it, but because of this compressive strength, those aren't really a problem structurally. So to think about engineers being able to create something, one, so beautiful, but also something that could last so long and be so durable is pretty amazing, and that makes it my favorite. Okay, as always, we are going to post all of the sources that we used for this. We'll be posting a number of Marie's articles as well as her blog in the show notes, so that if you are interested and want to learn even more about Roman concrete and how we are rediscovering it, you can go and explore that. If you have any questions or feedback for us, please send us emails at materialism.podcast@gmail.com. Make sure you subscribe to the show on iTunes, Spotify, Google Play, or wherever you find your podcasts. And if you like the show and want to help us reach more people, consider leaving a review. It helps us improve and it exposes us to more people. Finally, check out our Instagram page at materialism.podcast. We post a lot of interesting little arts and designs that relate to the episode contact, and you can connect with us on there to let us know what new material you'd like to hear about next. Next, we'd like to give a shout out to Alphabot for allowing us to use his music within the podcast. You can check him out on Spotify. And as always, a special thanks to Kolobite, who created the intro and outro for the podcast. He makes a ton of really cool synthwave music, and you can check him out at kolobite.bandcamp.com. Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.